Hi there, I'm Shubham Agrawal. I'm a PhD student at Australian National University working with Caroline Eakin. And today I would be talking about the work I did to estimate the sediment thickness within South Australia, and which is and it's titled Uncovering South Australia, the Passive Seismic Way. And this work was done in collaboration with John O'Donnell from Geological Survey of South Australia. And we recently submitted this manuscript to BSSA with the link, with the DOI just mentioned here. So first, I would like to start with a bit of a motivation setting up why do we need this. So in the 21st century, as we move away from fossil fuels towards renewable energy, more and more countries are developing infrastructure for renewable sources. And as the demand is increasing, there's the demand for the critical metals, which is the base metals, is also increasing because that goes in the infrastructure. And also it goes without saying that the Australian economy depends quite heavily on mineral and energy resources. However, it has been hypothesized, or like a growing consensus is emerging, that the mineral exploration frontier now lies beneath the post-mineralization cover. And on the figure in the right here are some of the major mining mineral deposits which have been found in Australia. However, the problem that lies is that 75% of the Australia is covered by Phanerozoic sediments. So uh, it it does begs the question that to look deeper, we need to first find the sediment thickness, which brings me to the motivation. As I just mentioned, that sediment thickness or estimates of that are crucial information. But the problem is uh, the current methods could be prohibitively expensive, especially in remote areas. Further, in the past 4 or 5 years, there is a growing um, awareness within the community, which came across as the Uncover Initiative to estimate the sediment thickness or to learn more about sedimentary history of Australia. And in this talk, um, I would try to I would try to showcase a method, a receiver function based method to determine the basement depth or the sedimentary thickness. And we make use of passive seismic techniques using temporary and permanent seismic stations. And further, I demonstrate the applicability of this method to South Australia. But why South Australia? And there were three reasons. First, South Australia has a continuing sedimentary history from 1.4 billion years ago to going on in the Cenozoic in the form of Murray Basin and Lake Eyre Basin. And one of the good things about South Australia is there are regions where there's no sediments, and there's regions where there are multiple sedimentary layers on top of each other. Secondly, South Australia has an extensive network of seismic stations with 12 temporary and 2 permanent. Out of these 12 temporary, two recent ones, Lake Eyre Fighter, which is partially funded by AuScope, and there is the new AusArray South Australia. And these two have enhanced the coverage. So in total, I used 243 seismic stations. And thirdly, there is an extensive borehole measurement database. And this is because South Australia is quite focused on energy. And more than 27,000 boreholes, onshore boreholes have been drilled with the depths ranging between 0 to almost 3,700 meters. However, something interesting to note is that out of these 27,000 boreholes, almost 26,000 have been drilled with where sediment thickness is within 200 meters, and which makes sense because drilling boreholes is expensive. Therefore, is there a better way, or not a better way, but is there a cheaper way to find sediment thickness using seismic stations? And the answer is yes. And the method, as I mentioned earlier, is receiver functions. So receiver function are one of the most effective and commonly used tool in passive seismologies to image the seismic discontinuities within the Earth, and they have been used extensively globally to find MOHO, or the lithosphere atmosphere boundary, or the 410-660 discontinuities. So to just shortly give a notion of how it works, let's imagine if there's an incoming P wave from a distant earthquake, And when it interacts with the sediment crust boundary, it undergoes a conversion from P to S. And as this P wave moves towards the station, it gets progressively more and more vertical because it's going through slower and slower material. And when we see this on the receiver function, what we see here is that the top here is the vertical receive function and the bottom is the radial receive function. This direct P has almost little to no energy at 0 seconds. And the first prominent peak that we observe on the radial receiver function is this P converted to S, which I call PSB. And if we can measure this difference between the P and the PSB, it might tell us something a bit about the depth of the sediments. And this is what I do for all the 230 stations, 243 stations that we are using. And what we got here is a map showcased on the right. So all the stations are colored by the TPSB values, the delay in the phase. And when we first saw this, we were quite amazed because it is a first order measurement, but it is already trying to tell us a story here. And what we see here is that the low values are quite well matched with regions of little to low sediments, which are the gray shaded regions of Musgrave Province, Collar Craton, and the Adelaide Rift complex. And the higher values, which go up to 1.3 seconds, are in the northeast parts of the state where there are multiple sedimentary basins off top of each other. So we see that this is useful information, but how do we make use of this information? And this is where the borehole database comes into picture. So if we can establish an empirical relation between the receiver function measurements and the borehole, we might be able to calculate the sediment thickness at any place in the world. To do that, first we calculate the borehole depth beneath each stations from the database, and we use something called inverse distance weighting. So on the plot here, the y-axis is the borehole basement depth and the x-axis is the arrival time measured at each station. So to calculate the borehole depth beneath each station, we take a weighted average of the surrounding boreholes to the stations where the weights are the inverse of the distance. And essentially what it does is for each station, it takes the borehole values surrounding to it. And in this plot, we can already see that there is some sort of trend. Also, I should mention that they are colored by where the stations are situated, either on Proterozoic basins, which are older than 500 million years, or the Phanerozoic basins. And if we bin this data by medians, which are these squares, and then regress this using two straight lines, we get these two equations. And I use these two equations to estimate the basement depth using the TPSB values. What we get is something like this. So again, the background is the borehole basement, borehole estimated depths, and the stations are colored by now what we empirically determine. And we see here that there is a close relationship between what we have estimated and the borehole basements, and they resemble quite well actually. And further, we improve the borehole, the geographical coverage of the basement. And then if we compare this with the sedimentary history basins, it further solidifies our notion that what we are getting is actually quite close to what there is. So if we look a bit more closely, to the highest values are towards the northeast, where there is the Warburton Basin, the Lake Eyre Basin, the Cooper, Aromanga are all top of each other. And as we go from the east to the west, here we see that the sediments thicken as we enter the Musgrave Province. And the similar pattern is seen here as well. But one place where it doesn't match is on top of the Caribou Basin, which is the 1.4 billion years old sedimentary basins. And we see here that the stations are estimating quite thin sediments. However, the borehole basement suggests the sediments are thick. And why could this be? And this is because that Proterozoic sediments are heavily metamorphosed with velocities greater than 6, which is hardly differentiable from the crust itself. So what we are measuring actually could be the top of Proterozoic sediments and not the base of Proterozoic sediments. And this is important information because sediment-hosted base metals are generally hosted in these Proterozoic basins. So even the information about the Proterozoic sediments could be quite useful. In summary, we have developed a novel way to estimate the depth to basements in presence of various sedimentary thickness. We use receiver function, and within the receiver function, we look at the arrival time of P2 as converted phases. And all of this is done without prior information about the velocity structure. And I will leave it here. If you have any questions, please feel free to contact on the email, and the prepend could be accessed through the link there. Thanks.